we'll start. This class we're going to discuss instantaneous frequency. This is a very different, if not a totally new view of frequency. We know our previous definition of frequency is usually 1 over period. 1 over period means that you have to have a whole wave to define frequency. Now, what if you have a part of a wave? I mean, I do not mean that you only have one portion of a sine wave. The whole total data is portion of a sine wave. Suppose a wave, your data started from a part of a wave and end with part of a wave. Now, how about the part that it's not a whole wave? Can we define frequency? Yeah. So 1 over t definition is correct physically, but it's very crude definition. This definition, as I said at the beginning, it's like a velocity is defined by distance over time. There's this distance we have to know over how long a distance, yeah, and over how long a time. So the better definition of velocity is time derivative of the position, yeah, and that gives us the instantaneous velocity. The frequency deserves the same treatment, yeah. So this kind of definition is too crude, and it's only work for simple sinusoidal wave, and does not apply to non-stationary processes. Yeah, a wave, a period, maybe first part of a wave can be shorter period, and later part can be longer. In other words, a asymmetric wave. How to define that frequency? So, and also it does not work for non-linear processes. I have a square wave. I have a sawtooth wave. I have a sine wave. They have the same period. And that, even though they have the same period, the physical and mathematical property of the wave are totally different. So if we want to describe this wave by just one number, this period, as 1 over t, our description is too crude. But if you give some other descriptions, you have to use a lot of words to describe the saturation. But if you use instantaneous frequency, then you will be able to describe it much better. And also, this 1 over t period does not satisfy the need for wave equations. Later we'll talk about what are the wave equations. And so we have, other than 1 over t, there are many other definitions of frequency. Like in Fourier analysis, we define frequency. The frequency is the time variable going through a Fourier transformation, and that we transform the whole thing into a frequency space, and the frequency then is defined in the frequency space omega. That's one definition. This definition, as we have already discussed, the frequency will be constant throughout the time integration domain. Yeah. The other one is a wavelet analysis. Most people doing wavelet analysis would lead you to believe that wavelet analysis give you scale, give you color, give you this, give you that, but not give you frequency. Turns out that's not right. The wavelet transformation has two important variables. One is translation, the other is dilation. The dilation variable is a time, they are all in time, in terms of time. And the inverse of that actually gives you frequency. So you can actually define frequency in wavelet analysis as well. And the third one is Wigner-Weil. We will talk about Wigner-Weil later. Wigner-Weil is similar to Fourier transformation. And Fourier analysis, as we have discussed in the beginning, if I have a wave of this form, the Fourier analysis will not give you the change property of the frequency. They give you time, and the time is constant. So the constant time representation of Fourier, it's not very descriptive. It will not give you the detailed analysis of how the frequency change. Another difficulty for Fourier is that in Fourier analysis, it totally ignores the phase information. Yeah. For example, if I have 10 waves, 10 sine waves, and if the 10 sine waves of different frequency, and frequency 1, omega 1, and 2 omega 1, 3 omega 1, 4 omega 1, all the way up to 10 omega 1, I can add these 10 sine waves in different form, different way. The first one is that I add with all the maximum line up at the 2. If I add up this 10 wave, I will have oscillation at a very sharp one, and then oscillation. This form, the blue curve, means that I have a phase-locked sine wave. Yeah, the phase-locked sine wave give you constructive reinforcement. And if you add infinite many of these sine waves, all phase lock, you actually get a delta function. Yeah. Now, the other way that I can add this is that I can add all this random, add this 10 wave randomly. The phase is totally uniform distributed, totally random. Then I can add up this, the red curve. If I have infinite many of this, I can get a white noise if I have uniform. So you have the same number of sine waves. Depends upon how you add. And this addition, the only difference of the addition is the phase, relative to the phase function of the two groups. One is phase locked, the other one is it's not uniform. It's uniform. And you get a totally different representation. One is a white noise, the other one is a delta function. But both of this give you a white spectrum because you all start with the same number of sine waves. So in Fourier analysis, there's no distinction between the two. The Fourier spectrum at this, there's no distinction between the two. So because of that, so when we look at the Fourier spectrum, we have to be very careful about what it actually tells us. Yeah. Typically, the random wave means totally independent. Each wave is independent. That is a linear system, typically. And a phase-locked sine wave usually are coming from nonlinear differential equations. Yeah. Like a water wave and whatever. They're all phase-locked sinusoidal wave. So this is actually all different wave, randomly phased, and this is a wave of phase-locked addition. So because of that, even we got a Fourier spectrum, we still do not have the phase information in there. We can have a frequency resolution. But the frequency resolution itself, again, is a problem because here we have better frequency resolution, poor time resolution. We have very good time resolution, but a poor frequency resolution. Yeah. This is what we call the uncertainty principle. So the problem with integral transformation, this integral transformation does not only limit it to Fourier. And any integral transformation means that, the frequency cannot be a function of time within the limit of integral. Yeah. So, so the frequency could not find within the integral limit. It's constant, and because of this, when you use this frequency in a differential equation, the frequency does not involve in the operation. It's constant. So it's a jump out of the operation. But in a lot of cases, when you linearize the system, it actually works pretty well. Even though the frequency is not a function of time, it actually gives you final answer. When you add it all together, it still makes sense. And that is a very interesting property. Yeah. The other difficulty of this is, as I said, uncertainty principle because of the integration. Within the integration period, you cannot have time resolution. And so time resolution and frequency resolution cannot be determined independently it cannot be determined together to arbitrary position. Because if you want to have a better frequency resolution, you have to have a longer time. And if you have a shorter time, then the time resolution is good, the frequency resolution is poor. Yeah. Other than the above definition, there's another very theoretical and very interesting definition that is in the Hamiltonian system. In Hamiltonian system, you can define Hamiltonian in terms of generalized momentum and a generalized coordinate position and time. So then once you have Hamiltonian, and then we can, once you have the generalized momentum and the frequency, we can define a term we call the wave action. The wave action is defined as generalized momentum integrated with respect to generalized position through a total cycle, a whole cycle. You have to go through a whole cycle. So the action variable is an average. It's not a really time variable. Once you have action, then a frequency definition is partial derivative of Hamiltonian with respect to A. This is a definition of frequency. And this definition of frequency works pretty well for some complicated system. But unfortunately, this is not a data analysis method. This is a method to study the whole system. And the reason is that you have to first write out the Hamiltonian. Yeah. And Hamiltonian, anybody has experience in theoretical mechanics, you'll find that Hamiltonian is not that straightforward to find. Once you find Hamiltonian, the problem is solved. So lots of time is actually spent in define Hamiltonian. And Hamiltonian mostly exists in the low-dimensional nonlinear system. Yeah. It is not a method for data analysis. It's a method to understand the system. Yeah. So what are the methods that we can use for data analysis? Here are two more. I introduced two more. One is Tigger's energy operator. The other one is the period between zero crossing and extrema. Yeah. Both of these methods had been used by engineers. In fact, the Tigger's energy operator is actually, I did not pay too much attention to it because I think it does not work well until I met James Kaiser. James Kaiser is the inventor of Kaiser window, and he works in the data analysis for a long, long time. By the time that I met him, he's already retired from Bell Lab. Must be a senior fellow at the Bell Lab. And he called me, he says he liked the instantaneous frequency approach that I proposed, but he really would like me to look at this energy operator. Yeah, we'll see what the energy operator means. The energy operator is invented by Tigger. The reason that Jim Kaiser pushed this very hard is Jim Kaiser and Tigger, they were relatives. Their wives were sisters. Yeah. After Tigger died, Tigger actually, they both graduated from MIT. Yeah. when Tiger died, Tiger actually, after he finished MIT PhD, he stayed at MIT to be a professor. Then the department head want him to study something else rather than just spend the time in study instantaneous frequency and data analysis. Tiger said, well, I don't want to follow your advice. I will leave. So he left MIT, and he moved across town to Boston U. Yeah, he stayed in Boston U all the time. And his idea is very simple. He said that if I have any function, xt, any function, I define an operator. This operator is that if I have x, I will take the first derivative of x and square it, minus the second derivative of x times the variable itself. Yeah. He defined this as an operator. Give any function, I don't care. I take one derivative, I square it, I take the second derivative, multiply with it, and then take the difference. The reason that it takes a difference, it looks like this is a difference. Turns out this is actually the sum. Yeah. Because if you have a sine function, you take first derivative, sine function is still positive. Second derivative is negative. So if you want to add the two, you have to minus rather than plus. Yeah. So this, basically, the physical idea behind it is first derivative. If x is position, the first derivative will give you velocity. So the first term, the first derivative square is velocity square, is kinetic energy. Yeah. The second derivative is acceleration. Acceleration means force. Force times distance means work. So that's potential energy. So what the operator means is kinetic energy plus potential energy is the total energy. Yeah. So that's why he called this energy operator. So any function you give me, I will take this derivative and I will define an energy operator. That's fine. That's perfectly legitimate. Yeah. Now what follows has a little bit of problem. He said that suppose my x is a times cosine sine omega t. Yeah. Then if I operate on this function, you take the first derivative sine becomes cosine, so it's a cosine, a omega cosine omega t. So square becomes a square cosine omega t. If you take the second derivative, sine becomes cosine again. Yeah. Second derivative, sine, no, I'm sorry. Sine, first derivative cosine, second derivative becomes sine again. So sine multiplied by its position by sine, so this becomes sine squared. Yeah. And the minus sine change that minus, so you get plus. So it becomes cosine plus cosine plus sine. So that end up with a squared omega squared. Yeah. This is the total energy, all right. So he said, suppose I operate, instead of operating on the position itself, I take the derivative of the position. Yeah. Derivative of the position is already a omega cosine. So if I operate on that, again, I get back to a squared omega fourth. The only difference is that here, x dot has already had a omega outside. So when you square it, you get square. So with this, he said this, well, this is a good idea. If I operate a function, take the function, operate it, and take the derivative of the function and operate, then I get a squared omega squared, a squared omega fourth. So then if I divide this term by that term, I take the square root. What I got? Omega. If I take the square root of this and divide into that, then omega squared cancel what I got. I get a. So then I can have both omega and amplitude of a function. Yeah. Unfortunately, this function is not arbitrary. This function has to be in this form, a sine omega t. A is constant, omega is constant. If a is not constant, and if omega is not constant, the first operator does not give you that term. remember, if A is function of time, omega is function of time. You take a derivative of A, what you got? You first have the A dot sine omega t, and plus A cosine omega t. Then that omega is not a constant, so omega has to be dotted again. So the whole thing becomes much hairier, much more complicated than a clean division. Then he realized that. He says, well, I did not put a sign, equal sign. I put approximately equal. Yeah. How approximated it will be depends upon how complicated your function is. Yeah. And this function becomes, this approximation becomes very, very poor if the frequency or amplitude change becomes very large. And what time the frequency change can be large? The frequency change can be large when the frequency has intra-wave frequency modulation. That's within one swing, the frequency change. Yeah. Within one period, the frequency change. And that's precisely the nonlinear saturation. Yeah. And also, the amplitude change very much when the frequency, when this process becomes highly non-stationary. Yeah. And furthermore, this amplitude has to be very simple. For example, I have a very complicated signal. I may not be able to write simply like that. To be able to write in that form take a lot of doing, like whether your function has to be a intrinsic mode function or whatever. Arbitrary function writing in this form has a very complicated A and very fast changing A and a fast changing omega. Yeah, we will see. So anyway, this is the method that is proposed by Tiger. And Tiger, he has a very strong personality. He pushed this even though it doesn't work very well, and he pushed this all his life. Yeah. By the time he died, this method still did not caught people's imagination or attention. Then when Jim Kaiser get hold of this, Kaiser made it heroic effort to try to push this. So because Kaiser is a very influential person, so he went to MIT, yeah, and find Quantieri. Quantieri works at MIT as an adjunct professor, but he actually work at the Lincoln Lab. Quantieri teach a course called speech analysis at MIT Graduate School. So all the people at MIT, you want to learn speech analysis, you take that course from Quantieri, and his book was published in 2000. It's called Discrete or Digital Analysis of Speech. I have a copy of the book. That's not enough. And he went to Harvard. At Harvard, he found a professor there, Monago. Right now, Monago is at Georgia Tech. But in the 90s, early 90s, he was at the Harvard University Applied Science Division. So one from Bell, one from MIT, one from Harvard. Three of them wrote two very long papers in IEEE. Yeah, they say the Tiger's operator works very well. Yeah. If you're interested, you can go back and look for this paper. Yeah, the paper basically explains how this thing works. Well, later we'll see how it works. This is the basic idea. Still another one is called the generalized zero crossing. Zero crossing has been used to define frequency for a long, long time. Before we have fast computer, the frequency mostly were defined by zero crossings. So you have a signal, it just comes to zero. Yeah. Now this is a very dangerous operation because What if my signal has many, many extrema before you cross zero? There are many more extrema than zero crossings, in a generalized, a general signal. But because of that, the one that push zero crossing approach actually is again from Bell Lab. It's S.O. Rice. S.O. Rice is a giant in data analysis in the 30s and 40s. S.O. Rice, his paper in random signal analysis, it's now classic. You can go any place, you can find his paper, originally published in Bell Lab journals, but now I think even appears in the collection of data analysis book. What he did was that he knew what he's talking about. He said that this method works for narrow band. Yeah. What do you mean by narrow band? He gave a very strict definition. Narrow band means the signal will have same number of zero crossing and extrema. Yeah. If you have the same number of zero crossing and extrema, then the multiple extrema is out of the way, so it's no problem. Yeah. So how do you do that? What he did was bandpass. I have a signal, I bandpassed it. If I take narrow enough band, I will have the same number of zero crossing and extrema. Yeah. And the kind of discussion that he has is mostly narrow band signal. So for narrow band signal, this method works to a reasonable degree of approximation pretty well. And in fact, many people in water wave study, so when people try to understand the surface wave, they immediately thought of this as a random signal. So at the beginning, all the people study water wave statistics, all borrow S.O. Rice result. S.O. Rice studied random noise for telephone company, for Bell Lab, because when you receive phone, it's always noise. And we have to understand where the noise comes from. And try to understand the noise is the initial push for many, many very profound physical and mathematical studies. S.O. Rice is a mathematical study of random noise, and that was borrowed totally by water wave study. Yeah. Water wave, instead of modified, just change the noise to wave. Everything works. Yeah. A different approach to study noise is to study where the noise come from. And so the Bell Lab sent two engineers to look for the noise signal. And that ended up in a Nobel Prize by Tanzak and Wilson. Yeah. They used a 3 millimeter radar to look for the noise, and they found the noise is uniform. So there's uniform noise residual in the universe. And they were puzzled. Then they went to Princeton. The Princeton people says, well, this is exactly what we're looking for, the Big Bang residual. Yeah. And so they get the Nobel Prize for that. So you see, study noise is a very productive area, even though the noise looks like irrelevant to, or it's something that we don't want. Turns out it's very important. Anyway, now if we want to study zero crossings, in the past they only study zero crossing. Why they only study zero crossing? They do not study the extremas. S.O. Rice established a theory. He said that the expected number of extrema in a data, it's proportional to, this is even narrow band, it's proportional to the fourth moment of the spectrum divided by the first moment. Fourth moment of the spectrum means the spectrum S omega multiplied by omega fourth integral. That's the fourth moment. Many spectrum blows up, has no way to evaluate, because once you multiply the fourth moment, the spectrum, suppose the spectrum is minus fourth, the multiply by fourth becomes constant. Constant integrates infinite, right? Now, if the spectrum, even the spectrum is the fifth, minus 5 power, multiply the force becomes 1 over omega. 1 over omega integrate becomes log. Log omega still, when you integrate from 0 to infinity, when omega becomes infinity, still blow up. So up to the fifth power, blow up. Not many spectrums steeper than 5. Yeah, many, like white noise is 1. Of course, 1 blows up right there. Red noise, whatever, all the noise actually blows up. So no one wants to study extrema. It's too much trouble. Yeah, but the narrow band means extrema equal to zero crossing, means force moment equal to second moment, and that's a very, very rare condition. And the only thing that you can satisfy that condition is almost a line spectrum. Yeah. So if you want to do what is the zero crossing probability density function, the expected number of zero crossing for a signal is actually second power of the spectrum. Is proportional to second power. Second power is much easier to get a finite value. So most people say, fine, we just do zero crossing. Yeah. In this study, I apply this method to IMF, to intrinsic mode function. The extrema already equal to zero crossing. Yeah. Not only that, this function, in terms of intrinsic mode function, is not exactly narrow band. The force moment is not equal to the second moment square. Yeah. So this is a odd function. It's very different from what S.O. Wright studied. But here, we defined zero crossing. Instead of just using zero crossing, I use it as a generalized zero crossing. Generalized zero crossing means that I use the function not only just look at the 0 point. I look at all the critical points. The critical points, by definition, are the zeros, x equal to 0, and x prime equal to 0. X prime equal to 0 are the maximum, minimum points. So I took all the maximum, minimum points and try to define frequency that way. Now, the way that I define that is like this. When you have both maximum, minimum, and zero crossings defined, you just define the interval between the different critical points. Yeah. Then we can measure this distance. We can measure this distance, measure that distance, measure this distance. And each of this distance equal to not the whole wave, but a quarter of a wave. Yeah. Then if I skip one, I will measure what? I will measure a half wave. I will measure only the wave trough, peak, or wave trough, or between the maximum to minimum, or between minimum to maximum. So this will be half wave. Then if you skip 4, then you have this color is very light. You can have from up zero crossing to next up zero crossing. That's a whole wave. Yeah. So at each location, at any location, what you find is that I can only have one quarter wave, 2 half wave, and 4 full wave. Because any wave, any point, I can count this wave, I can count that wave, I can count 4 different times of wave. Now because of that, so my definition of frequency, we can define it as 1 over T1, which is quarter wave. Then quarter wave, the frequency is not 1 over T1, it's 1 over 4 times T1. Yeah. And if I use half wave, it's 1 over 2 times T2. And only full wave, it's 1 over T. Now for this different definition, which one should I use? Yeah. So my definition is that I will average them. Not only I will average, I will assign different weight to this definition. The 1 over T1, the quarter wavelength, is the most local definition. Even if the wave can, say, have this situation, that is, I have a small wave followed by a large wave. Yeah. If I count this wave as part of this, then the period is much longer. If I consider this wave to be part of this, the period is much shorter. Yeah. So, but if I consider wave only as this is much local. So I give this a more weight. Give the half wave less weight. I give the full wave the least weight. So the weight that I assign is that I have the definition of the F1, I give it the 4, weight of 4. F2, I get a wave factor of 2. And F4, I only give it just one weight. So in this way, then I average the frequency. Then I have a more stable and more representative instantaneous frequency. So the final instantaneous frequency is 4 times F1 plus 2 times 2F2 plus this. So the total weight is 12. Then I divide by 12. So this is the two-way to define instantaneous frequency. Here, Tigger is very good super time resolution, because you see Tigger, even though it has all the problems, but it defines frequency by derivative, and derivative of the data only at that point, second derivative, at most third derivative. So third derivative you get about 4 points, local, so it's extremely local. Generalized zero crossing is not very local, but it's very robust. What do you mean by robust? It cannot be wrong, but very large. It's very stable calculation. The reason is that generalized zero crossing is basically 1 over t. Yeah. Instead of 1 over t, I made that t a little bit finer. Yeah. If there's any way to define the finer, I will use it. But from the data, the only way that I can define is using zero crossings and extrema. So this is very, very close to 1 over t. Yeah. So in the mean, if the value come of the mean is different from generalized zero crossing, the value cannot be right. So generalized zero crossing is the most robust, but even though it's crude, but in the mean it's always correct. So if I derive any function, and the instantaneous frequency deviate from the generalized zero crossing the mean, it cannot be right. Another thing is that when you compute the frequency, and when you compute the frequency to be within 1/4 wave, that's already better than any of the methods that you can have. Like a Fourier is from beginning to end. Spectrogram, spectrogram cannot get inside the wave. Spectrogram still have to have a few waves in order to define frequency, because it's Fourier transformation. Yeah. So none of the past methods give you frequency resolution better than single waves. It's absolute obvious, absolute no. But here we get into quarter wavelength. That's already better than any of the other methods that I know. Yeah. So that actually gives you a good solution. But it even gives you a little bit of hint of intra-wave frequency modulation, because of front and back. But once we went through the average, then most of the intra-wave frequency modulation get averaged out. Yeah. So the generalized zero crossing, it's still a very useful method. And then we have another way to define frequency. That is use Hilbert transformation. Yeah. Hilbert transformation means that if I have x, I decompose AT over EI theta t, then omega is defined time derivative of phase. Yeah. That is a definition that when I first started, I use. And that's why this method, it's the method that I developed, is designated as HHT. Yeah. H is for Hilbert transformation. But the more I use this, I find there are problems. So later, I decide to go a step further, called the quadrature method. Yeah. The word quadrature is in English is a little bit has some problem. Quadrature by itself is a computational method, but the quadrature used by engineer is to try to find 90-degree phase shift. Yeah, quadrature is 90-degree phase shift. So quadrature method, we will use a normalized x and define y, and then use arctangent y over x, then define phase. Instead of using Hilbert transformation, we use the real and the imaginary part. We will discuss this in detail. So instantaneous frequency is very different, but we do need that. The reason we need that is that in the wave study, in water wave study, we usually, if you take any theoretical book, you find the waves defined as a phenomenon that has a phase function. And phase function is gradually changing so that the time derivative of phase gives you frequency, spatial derivative gives you wave number. So you cross differentiate, you have time derivative of wave number and the spatial derivative of frequency, the sum is 0. This is called kinematic conservation. I don't care what the omega is. I don't care what the k is. But the idea here is that the omega and k has to be differentiable. If it's differentiable, it means that it has to have instantaneous value. Now, if we take Fourier frequency and wave number, we put it in here, it is satisfied, of course, because wave number and frequency are both constant. So constant 0 plus 0 is 0. So it does not violate the kinematic conservation, but it's a trivial satisfaction. Yeah, it satisfies the equation in a trivial condition. And for physical study, we'll study the meaningful thing, we'll not study trivial cases. Yeah. For general case, the frequency and wave number should not be constant. We'll see later. Even though the instantaneous frequency is meaningful, it's asked by mathematics, asked by physics, but still there are people against this. The one that the person against this is Schickel. Schickel said the term instantaneous frequency should be banished forever from the dictionary of communication engineers. He was a communication engineer. In 1953, he wrote in IEEE. At that time, it's not IEEE, it's IER or IRE. I forgot which way they called it. Mostly IRE, Institute of Radio Engineering or something. He said that we should not even let the word instantaneous frequency exist. So we should banish it, should get rid of it. That, of course, is old-fashioned. Let's look at something new. 2001. 2001, in Granting, he wrote a book called Mathematical Foundation for Time Frequency Analysis. Yeah. And in there, he said, the uncertainty principle makes the concept of instantaneous frequency impossible. Yeah. It's the whole idea that he had was that if we use Fourier analysis as a base to do time frequency analysis, then instantaneous frequency is not possible. Because if you use Fourier analysis is integral transformation, then by the virtue of integral transformation, time and frequency cannot be determined both precisely to an arbitrary degree. If you cannot define both to arbitrary degree of precision, how can you talk about instantaneous value? That's not possible. This is true, but the only thing that this is true is because he used integral transformation. If you do not use integral transformation, then the uncertainty principle is not there. Yeah. So both of them has a certain part of truth, but I don't think they actually realize from what point of view they made that statement. Yeah. Now, the ideal situation to get instantaneous frequency is that you obtain an analytical signal based on real value functions through Hilbert transformation and compute the instantaneous frequency by taking derivative of phase function. Yeah. This is true only if the function is IMF. We know that if function is not IMF, we have problems. Yeah. But even if we do that, so what? Even if we try to go through to find IMF, we are still not totally out of the woods yet. The reason is that the data must be expressed in terms of an intrinsic mode function. Once you get intrinsic mode function, yeah, the IMF, intrinsic mode function, is only necessary. It still does not totally satisfy the condition because there are two more barriers in front of us. One is Bedrethin, the other is Nato theory. Yeah. So the simple derivative of the phase does not work at all. Even if simple derivative of the phase function from RMF may not even work. So this is very serious. That means at the beginning, I was naively believed that if I decompose it, I will get it. But it turns out it's not. So for example, if I have a hello, if I use the hello to take a Hilbert transformation, this function becomes that. And that's almost chaotic. And if you take a derivative, this is the function, the derivative looks here. Look at all these large fluctuations, and many, many negative number and fluctuation. This kind of instantaneous frequency is meaningless. Yeah. Empirical decomposition. After empirical decomposition, we still have problems. The first problem we encounter is Bedrethin theory. Bedrethin theory says that when we use Hilbert transformation, we say that the Hilbert transformation, you take the Hilbert transformation of a function. You take the ratio of the function, you get arctangent. That is, if the function is a cosine theta, you take Hilbert transformation, you get a sine theta. How come the a is not involved? In other words, Hilbert transformation a cosine, then becomes a come out, Hilbert transformation of sine becomes cosine. So a is not involved. So Bedrethin immediately thought this inconsistency. So you say a is a function of time too, then a should be involved in the Hilbert transformation. Now, if you leave the a out, there must be some condition. So here is what the condition is. The condition is the Fourier transformation of f. If we have f and g, both are generalized complex variable, the Fourier transformation of fx is f omega, of gx is g omega. If fx is omega larger than a constant a, and this is if it's vanished, is gx is 0 for omega less than a. What it means is that frequency f omega and g omega are totally disjoint. Yeah, the f omega can only have value when omega is less than a. When omega larger than a, it vanishes, 0. Okay, and g omega can only have value when omega is larger than a. When omega is less than a, it vanishes. So f and g, amplitude and frequency, has to be totally separate. If they are totally separate, then the Hilbert transformation of f times g, we can take f out. F is not involved. The lower frequency component is not involved. We can only do the high frequency. This is Bedrosian theory. This is called the product theory of Bedrosian. And when it first came out, of course, it shocked many people. And this was a very short paper. It's only a page and a half in IEEE. And it was cited many, many times by people because it's so important. But immediately after that, however, Nuttall come up with another theory. Nuttall, I believe he's still alive. He is one of the group at MIT during the Second World War, started under Nobel winner in the radar study. Yeah. After he finished MIT, he joined the Navy, worked in the Navy. Most of his study are classified. Yeah. Occasionally, he has some paper published. He's a very smart person. I tried to meet him. I was invited by the Navy to give a talk about 7 or 8 years ago. I said, well, I'll come, provide you set up an appointment with me with Nuttall. This is no problem. He's here all the time. You come and we'll give you a whole afternoon to discuss with him. So I was very happy. I went. By the time I arrived, they say, oh, sorry. Nuttall was in the hospital, has a heart operation. He has a bypass operation. So I never saw him. I believe he's probably retired. Anyway, what he did was when he saw Bedrosian theory, he says, whoa, hold it. Even Bedrosian theory has a problem. Now what he did, let me first get a Bedrosian theory. Let me get a, here. This is a Nuttall theory and Bedrosian theory in more plain language. It says Bedrosian theory is A cosine theta, AT cosine theta t. We talk about A as a function of time, right? So might not be exactly A sine t. So this A, if you transform this cosine into sine, if the A is not involved. If A is not involved, only A and the cosine theta t, the spectrum must be disjoint. Bedrosian come up with a very fancy theory, but boiled down to the present language is this, is that let's forget about A. Let's say A is not there. Yeah, A is 1. Yeah, unit. Now, cosine theta t is the Hilbert transformation of cosine t equal to sine t. He says no. For arbitrary theta, this is not true. So that threw a big question mark in the Hilbert operator. Basically what he did in a very elegant way is this. He said that if I have any function fx, and if we have a quadrature, by quadrature means I have a function, and this function has a face, and I shift the face by 90 degrees, perfect 90 degrees. I'll call it quadrature. Okay, and the Hilbert transformation, of course, this function has a Hilbert transformation. You think Hilbert transformation might be the quadrature, but he said if x and q, are they really the same? Let's measure this. let's take x cubed minus xh squared, integral from 0 to infinity with all the possible time domain. It turns out this quantity is not 0. That means quadrature and the Hilbert transformation are not the same thing. Yeah. For arbitrary theta. And in terms of what? He proved this theory in terms of quadrature spectrum. Yeah. This is a very nice theory. I like it very much. It pointed out a problem, but practically it will not help us at all. The reason is that the data are not necessarily IMF. Even if we get IMF, yeah, IMF is only necessary but not sufficient. Bedressing add a requirement of having not very strong amplitude fluctuation. If amplitude fluctuates a lot, then the amplitude of the spectrum and the phase spectrum may not be disjoint. If amplitude is very slow, it's constant, for example, then it's okay. But that's based on Bedressian. The Nato theory said that the analytical function and quadrature may not be the same. Yeah. So, but this theory, why I say this theory is not very useful? Because the result is given in terms of quadrature spectrum. I have a function. The functions, the spectrum of the function I know. So the spectrum of the function, if I know the spectrum of the function, if this is in terms of spectrum of the function of spectrum of the function, I can evaluate. If this is in terms of quadrature, I'm looking for quadrature. If I have a quadrature, I don't have to do anything. I have the problem solved. But in terms of quadrature spectrum, this quantity is unknown. Even though we know it's not 0, but you don't know it. Okay. Not only that, even if you know it, this integral, it's from minus infinity to 0, it's a definitive integral. So it's come out a constant. So the whole arrow bar is a constant. If it's a constant, means the whole integral has this much arrow. It does not help us to point it out where the arrow is. Yeah. So for a non-stationary process, you give me one overall value. That's not going to help me. So what are we going to do? We get stuck. We get stuck is that for x, if we get y through Hilbert transformation, this is analytic. But analytic, we know analytic is not correct because of Bedressian and Nato. But if we want to find the quadrature, there's no general method to find the quadrature. Yeah. For generalized function to find the quadrature, it's not known. So the difference is that the analytical function satisfies Cauchy-Riemann equation. We're not playing mathematical game. Cauchy-Riemann equation is a very beautiful equation, but it's not going to help us. What will help us is that the x squared plus y squared has to be equal to 1. That's the requirement for quadrature. That means sine, cosine. That means I can get arctangent to get the original way. But it's not. So the arctangent cannot recover the theta. Analytical function is not x plus y squared equal to 1. But quadrature pair is not analytic. However, this is the exact 90 degree. So it's x squared plus y squared equal to 1 if we normalize it. So we get stuck. So we have to normalize it. Yeah. So how to normalize it? We can see that, suppose we have a IMF. This is IMF. Why I know this is IMF? Because I started with a sine function. A sine function multiplies step function. Sine function multiplies step function is very small and suddenly jump very large. Yeah. The step function I multiplied is actually not a very good step function, exactly sharp. I have even a ramp. Yeah. So this is by any standard, This is the IMF. So I take this as well. This is IMF. Okay, I'll do a Hilbert transform. I look at what happened is that this step function, the carrier is one frequency. But step function spectrum is very wide. Yeah. So for this function, the envelope spectrum is a ramp. If I have a delta, my function is a white, so it's cover every frequency. Step function is delta function integral. So step function has a generalized, has a general a power law, -1. It covers every frequency. So the envelope and the carrier, the frequency, the spectrum is not disjoint. They have the same value here. So it violates Bell-Jackson theory. Let's see the consequence of Bell-Jackson theory. Once you violate that, what happened? The Hilbert spectrum looks like this. This is a very ugly Hilbert spectrum. Yeah, the frequency oscillate large and small. Not only that, it has some value even negative. We have already said that once I get the IMF, I should be able to get all positive. It does not. It will not even give you the right value. The right value is here. So if I got a Hilbert spectrum like this, I would not be very proud. Yeah, because this is worse than the wavelet analysis. The wavelet analysis at least gives you the right frequency. The amplitude is low, the amplitude is high, and basically constant. Even though we know the end effect and we know the transition, they are all okay, but it does not give you value like oscillate like this. Yeah. So when you encounter this kind of problem, you find that the HHT does not work. Yeah. Now, even spectrogram is better. The spectrogram is constant. Even though the resolution is not very good, but at least it tells you the frequency is constant. Yeah. We do not even have frequency constant. The frequency oscillates that much. Yeah. So, but if we normalize it, then we find the frequency is constant. The previous function indeed has a constant frequency, because I started with the sine function, cosine function. So the problem is that we have problem. The instantaneous frequency cannot be just computed. Give me the IMF, I immediately computed the frequency. Yeah. So normalize. Normalize is effectively an empirical way to decompose the signal into a FM and AM. Amplitude fluctuation and frequency fluctuation. If we can achieve that, then we get one step closer to the true answer. At least we can get rid of Bell-Jackson theories, limitation of Bell-Jackson theory. By the way, I have to mention here, next time, or maybe I should give you a list of references. After I publish this paper, and after I publish the empirical mode decomposition, and I engage lots of mathematicians to get interested in the problem. The mathematician are mesmerized by the name of Hilbert, okay? But then they find the Bell-Jackson theory limitation, so they immediately try to defend Hilbert. So Hilbert has to be right. As long as we can find some way to diffuse Bell-Jackson, then the Hilbert still works. So they went out and find all kinds of functions that satisfy Bell-Jackson theory, and the Hilbert transformation is still good. Yeah. Still give you, by good means still give you positive frequency. So the mathematicians, there are tens, if not hundreds of papers by mathematicians say that I can find a function satisfy such and such property, it will give you positive frequency. I told them that positive frequency is not is not the only condition. It is again a necessary condition. If you get a negative frequency, then forget it. If you get a positive, it may be right. Positive frequency many frequencies, these are mostly positive. This is still useless. Yeah. So if you see a lot of the mathematical paper, try to find functional form satisfy Bedressian theory. Don't be misled. Mostly, I say, mostly are useless. The reason is that our function may not satisfy that condition. Our function is a very general function. Okay, so we want to actually do, FM, AM, AM, FM decomposition. So I proposed a normalized procedure. I will not go through this word description. Let me go through the methodology first, and then I will come back to look at the description. Suppose I have a intrinsic mode function, yeah, IMF. IMF fluctuates large and small, large and small. Yeah, but this, the large, it's AM fluctuation and also FM fluctuation. The AM fluctuation, FM fluctuation, most likely could not be separated. Yeah, and what I did was I take the absolute value of the value. This function, I take the absolute value. All the negative value becomes positive. So I get this value. And out of this value, I identify all the maximums are given by the red square. I connect all the red square, red circles with a spline function. Then I divide the spline function. I divide the number by the spline function, E1. That gives me F1. F1, because by division, so all the maximums has to be 1. Yeah, so the maximum becomes 1. Will that solve my problem? Most likely it should, but occasionally it does not. The reason is that when you do spline, you may cut into the data. So once is not enough. Then you can do it the second time. Take F1 and normalize it again. And so F1 equals E x1 over E1. So this becomes x1 E1 times E2. And you can do this infinitely many times, or finite times. Eventually, you definitely will find that everywhere is less than 1. Once you get everywhere less than 1, and the maximums are all 1, and that is most likely it's a sine function. We can write it in terms of a sine cosine. So the final form is x1 divided by E1, E2 to the En. So Ft is the empirical FM signal. Yeah. Then E1 times E2 is the empirical AM signal. So we have FM, AM decomposition. Here is the signal. This is the original signal I give you. And if you go through the normalized once, so what happens is that you still have some point which is not 1. The reason it's not 1 is that when this curve comes down, it actually cuts through some of the data. So when you divide that, then it becomes maximum. Yeah. And actually, not only maximum, it's more than 1. But if you do it another time, then the second time around becomes the green. The green is all fine. Yeah, everything's less than 1. So when you take this data, and if you compute the instantaneous frequency, use Hilbert transformation, what you got? You get the green curve. The green curve has lots of places go very large, and also certain value has very large deviations. When you normalize it, so what happens? To normalize it becomes a red. Even though this number can still be big, but it's never get negative. Yeah, and indeed this frequency is very high, and see, for example, even this place get more manageable. Yeah, this is the normalized effect. And in terms of phase, the original phase function is because the amplitude becomes large and small, it swirls around in the big wild region of the phase plane. But if you normalize it, the amplitude is very close to 1. Remember, normalized, they are still analytical function. Analytical function x plus y, it's not 1. It's still not 1. So it's not exact. If it's 1, it's a pure circle. This is still not a pure circle. So it still fluctuates. And because x plus y, even after you normalize it, you compute the Hilbert transformation. Because the Hilbert transformation, if you code your function sine, the Hilbert transformation cosine, right? Because sine, cosine, the sum is not 1. That means it's not exactly sine-cosine relationship. Yeah, and that's why it's not exactly does not add up to 1. So this has a problem. Where the problem comes from? The problem, if you compute x squared plus y squared and minus 1 to see where are the errors. See, the error comes mostly here. When around this region, x plus 1 is not 1, and deviate from 1 by 25%. And all the other place, this place, they are all when x squared plus y squared is not 1. Yeah. In fact, nowhere it's equal to 1. Everywhere it's deviate from 1. But from 1 it's very tiny, some small, sometimes large. Okay. So this is a better indicator for errors. This error function is a function of time. It's not a constant. Yeah. It's an error function of time. Then could you plot the constant limit given by Bajorasian theory? The answer is no, because I don't have quadrature. I don't know the spectrum. Yeah. So look at this. Look at where the error is. The error occurs very large. Look at this function. This function is not exactly a sine function or cosine function. It has a deviation, a deflection. So that indicates Hilbert transformation is not really a very good way to do instantaneous frequency. Yeah. Whenever the function has some deviation from the pure sine, you have such large error. Yeah. You come over here, you also get a large error. Here, you also get a large error. Anytime the function is not very smoothly sine, cosine, we always have problem. That is the downfall. That is the limitation of Hilbert transformation. Yeah. We all get error. Notice, however, this error does not imply the instantaneous frequency is so bad. At least it indicated the amplitude is not correct. Yeah, because x squared plus y squared is not 1. So once you have the amplitude, so the amplitude can be decomposed. This AM. Here is the FM component. This is the AM envelope. The AM, I'm sorry. This is the FM signal. This is the AM. So the amplitude AM, the amplitude of fluctuation also has time scales, has different time scales. So we have FM and AM spectrum of a signal. That is a complete description of the function. So now let's see the procedure. The procedure is the following. Getting IMF, yeah, and find the local maximum of the absolute value and construct a spline SE through maximum. Then if the envelope go under the data, we will do it again. And so finally, the data is data divided by the spline, empirical spline. And this step can be repeated. And then after that, we compute the instantaneous frequency. We also compute the absolute value of Hilbert transformation. Then the absolute value of Hilbert transformation minus 1 square is the error index. Yeah. So here it's the procedure. For example, if we have a model function, cosine chirp, cosine t over 512 cubic, yeah, we have an exponential decay. Now, what would this function look like? This function looks like very large, and exponential decay is very small. Yeah. Is this a function IMF? The answer is yes, because look, this function is a envelope times a cosine function. Cosine function is perfect symmetric. Yeah. Okay, so this function, if I want to normalize it, I first find the absolute value maximum, and I spline through the maximum. So this is the spline through, or the maximum point spline. Look what the problem is. The problem is that I cut through the data. Even though this is the maximum, this is the maximum. When I draw this, I cut through under the data. If I divide the data by this curve, this point is 1, this point is 1, but this point is more than 1. So that's why we have to do it more than once. But you say, oh, this is the problem is initiated by you. What if you use, instead of use the empirical envelope, what if you use Hilbert transformation envelope? Yeah. Take the function, do a Hilbert transformation, and take the absolute value of the Hilbert transformation. That's an envelope. How about use that envelope? That envelope actually is the green curve. And the green curve has a lot of problems. It does not really go through the data because of the N effect. Yeah, we will talk about that if we have time. But so, let's use this red and the green. Both use this to normalize. So what happens is that when you normalize, the original data looks like this. After you use the red curve to, red envelope to normalize it, we have some points bigger than 1. Yeah, but most of the wave looks decent. But if we use this curve to normalize it, look at what the problem we have. The problem we have is this. See all this wave? Instead of a sine wave, it's all skewed. Why it's skewed? Because the Hilbert transformation maximum does not line up with the maximum. Yeah. And with both of these methods has a problem. This maximum and this maximum, the maximum is displaced in the red one. Yeah. The reason the maximum is displaced is because the maximum now gets shifted to this point rather than the original point. So the normalization does have problem. But the Hilbert transformation maximum has even worse problems. The amplitude is not normalized at all. The reason is that it starts to tilt up. So if we use this tool to plot a phase plan, the normalized with empirical envelope looks more near circle, but the normalized with the original without normalized looks very poor. And when you compute the frequency, instantaneous frequency, without normalization, just compute the Hilbert spectrum, Hilbert transformation, we find that a simple function like that, we have a lot of odd value, not only odd value, some even negative and some even near 0. So it doesn't work, Hilbert transformation. If we normalize it, we alleviate the problem a little bit here, but again, this part is still bad. Now here, if we say, forget about all this fancy stuff. Let's just use zero crossing. Yeah. Look at the zero crossing. Constant, step, 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 step. Come up there. And that is very close to the truth. The generalized zero crossing. It's robust. It's pretty close to the truth. Yeah. And if we use Tigers operator, the Tigers operator is very nice here. Very nice, except at the beginning. Yeah. So here we have a comparison with a very simple equation. We find that different value, different method has a different solution. The errors are obvious. If we use the empirical spline to normalize it, we get the decent value here, but not very decent value at the beginning because we have that problem. And using Hilbert transformation to normalize it, it does not work at all. Yeah, in most of the case, the instantaneous frequency has errors. So quadrature. Now let's try a different way. Now we have a function which is a Duffing pendulum. Duffing pendulum means cosine omega plus epsilon sine 2 omega t. And Duffing pendulum, we have met this equation many times. The form looks like this. And if we use Hilbert transformation, what is the Hilbert transformation of this blue? The blue is our data. If we use Hilbert transformation to compute the imaginary part, we get this red curve. This red curve is Hilbert transformation. This green curve is actually the quadrature. In this case, we know exactly what the quadrature is because I just changed this cosine to sine. It's my quadrature. Exact 90 degrees. No argument. Right? So this is the cosine function. This is the sine function. This is what I try to get the sine function through Hilbert transformation. So what we got, we find that we got it almost right, but not quite right. Yeah. Now we see if we compute the x squared plus y squared to try to find the amplitude. X squared per y squared, the red curve come out to be exact 1. Sine plus cosine is exact 1. No argument. But if you compute the blue plus the red square, which is the function plus its Hilbert transformation, what we got is this function. It's not always 1. It's always near 1, but it's never be 1. Okay. So another way to do that is Tigers, of dear friend Tigers. If we use Tigers operator, operate on this function, we take a derivative, a second derivative, multiply, and then divide and all that, we should get a amplitude. So the Tigers amplitude is this. It's correct only at one point, and not every point, but every other point, it's perfect. Or the rest of the place is terrible. Yeah. So the Tiger does not work for nonlinear waves. Yeah. Anytime you have deviation from linear sine wave, Tiger has a problem. Why? Because the omega changes so fast. The approximation no longer works. The amplitude, when you plot the phase function, the quadrature gives you a perfect circle, 1. Yeah. The Hilbert transformation gives you this. The difference between that indicates error. as an indicator for error, but that indicator is only on amplitude, not on frequency. So if we compute the instantaneous frequency, now we see the problem of each value, each method. This is the quadrature method. This is the truth, as well as quadrature method. Yeah, they are the same. This is the Hilbert transformation. The Hilbert transformation will never get to the truth, but it's almost the truth. It gives you the correct fluctuation, but not enough depth. Yeah, we're off by that. So if we use zero crossing to get the value, the zero crossing gives you constant value. You say, aha, constant value is ugly, but constant value is almost right. Because you average this, you get exact that value. Yeah. So in the mean, the frequency is correct. It does not give you the intra-wave frequency modulation. So the generalized zero crossing is still very good. Compared to what? Compared to all the other values. Now we see, where's the Tigers energy operator? Tigers energy operator, it gives you this. The frequency is totally wrong. Yeah, using Tigers energy operator. You will be right only here, only here. Yeah, all the other points, it's completely out of question. Yeah, so the quadrature procedure. So how to compute quadrature? You use 1 minus x squared to y. So x squared plus y squared, by definition, is 1. Right? So there's no escape. Yeah. You normalize this is 1. The minus square get a y. Yeah. So x squared plus y squared is 1. So y over x is arctangent. So that will be quadrature. That's our definition of quadrature. Yeah. So we have all this value. We can try different cases. This is the case when we have amplitude fluctuation, cubic chirp, and then a Duffing pendulum. So this has a lot of complication in there. And if you look at the envelope and the carrier frequency, there are a lot of places. See, this is the amplitude. The amplitude and the carrier is not totally separate. So Bedrosian theory already limited our answer. Yeah, and if you look at the original function in phase plan looks like this because the amplitude keep decreasing. It looks like this. But if you normalize it, it gets to this function. But this function is still not quite 1. But if you use quadrature, once you use quadrature, it will give you perfect circle 1. And when you compute the amplitude of the function, you find that this is our signal. This is your data. The quadrature gives you this. Quadrature gives you the red. Yeah, and Hilbert normalization and the Hilbert transformation gives you this. Hilbert transformation doesn't work at all because of the N effect. And if you use Hilbert, normalize the Hilbert, it almost follows the function, but it's not not exactly the quadrature. And the amplitude you got from this, you find that using zero cross, generalized zero crossing, gives you step function. It's generally follow the curve. Yeah, and using the other normalized value using Hilbert normalized, you get off. But if you use the other normalization, it generally follow the function very well. And instantaneous frequency, at the beginning, you already see the Hilbert transformation give you a little bit off answer because it's not deep enough. And over here, you find that the Hilbert transformation is totally wild over here. not good at all. Yeah. The function here show that this is just Hilbert transformation. This is the generalized zero crossing. Generalized zero crossing still goes through the mean. So generalized zero crossing is still highly usable, even though it does not give you the fluctuation. The Tigers method, it's absolutely out of the question. It cannot be used at all. And Hilbert transformation gives you a smooth function, but not deep enough. If you use quadrature, occasionally you have a little bit off because the data, by the time you get a very high frequency, the data is not enough for you to compute the quadrature accurately. Yeah. This is the general comparison. I think we are a little bit over our friends in Tokyo, maybe a little bit anxious. So I will stop here. We'll pick up next time and continue. So the class will stop. Say, hello, our friends in Tokyo. You have any questions? Any questions? Oh, no question. All right. If you have no question, we'll stop here. We'll pick up next time. Remember, November 25th is the day off for us. We will not have a class on the 25th. Okay? So the next time will be the 28th. This is 28th or 27th? 28th, yeah. No, 26th. 27th. So next Friday we'll have a meeting. Hello, for all you. Even though I'm here, my wife's in Japan. She's in Kyoto, not Tokyo, Kyoto, as a tourist to see the maple leaves, the glorious maple leaves over there. So hi for all the you in Japan. And how's the weather there, by the way? How's the weather in Japan? The weather, is it clear? Is it snowy? Can you hear me? Huh? Can you hear me?
I think it's very cold, Professor.
Very cold? Is it sunny?
Yes.
Is it sunny? Huh?
Yeah, yesterday it was raining, but today it's very nice day.
Oh, nice day.
But yesterday it was raining all the day.
I hope it's a good day for tourists. All right, thank you very much. The class is dismissed. See you next time.